Let's see what is meant by page hit and page miss, right? Page hit. If the page containing the byte or word, see, we have not seen what is meant by word, right? We will see that a bit later. As of now, just assume that I mean only byte. Okay, I've just written this R word because after seeing what is meant by word, you will understand you will understand this clearly. As of now, just think that it is having only byte, but write R word as well. If the page containing the byte which CPU wants to access is present inside the RAM, then it is called as page hit. For example, let us assume we are using virtual memory concept. Okay, we are using virtual memory concept, and process P1 has 4 pages named as page 0, page 1, page 2, and page 3. And we are having only 2 pages, page number 0 of P1 and page number 1 of P1 inside the RAM. Page 2 and P3 are not present inside the RAM. Okay. Now, let us assume process CPU is asking for a byte which is present in either page 0 of P1 or the byte which is present in page 1 of P1. See, page 0 or page 1 will have lot of bytes, right? They will have lot of bytes. We have seen it. Now, the byte which CPU is asking for is present inside either page 0 or page 1, then it will result as a page hit, right? What do you mean by page hit? The byte which CPU is asking for is present inside the RAM, is present inside a page, and that page is present inside the RAM, right? That is what we mean by page hit. Now, in case if CPU asks for a byte which is present in page 2 of P1, then we say that as page fault or page miss. Okay, see this, page fault also called as page miss. If the page containing the byte which CPU wants to access is not present inside the RAM, then it is called as page fault. It is also called as page miss. Fine. See this. So CPU is asking for a byte, then that byte is present in page 2. Now if page 2 is not present inside the RAM, then what will happen is, then that is what we mean by page fault, right? Now how will we address this page fault? It is simple. We will move this page inside the RAM. After the movement of this page inside the RAM, CPU will fetch that byte. Okay, that is how page fault is actually handled. We will see that a bit later. Okay, how page fault is handled and all this, we will see that. Now, as of now, see, one thing you can understand here is, in case if the byte which CPU is asking for results as a page hit, the time taken to fetch the byte will be very less, right? For example, in case if CPU is asking for this byte, which means the byte which is present in page 1. Now, time taken to get the byte is very less because we need to access only the RAM, right? We need to get the byte from the RAM. Now, how many memory accesses, all this we'll see that later. As of now, don't come into that. But one thing you can understand is, in order to get the byte, I need to only access the RAM. I don't need to access the hard disk. But in case if CPU asks for a byte which is present in page 2 of P1, in this case, see what CPU will do is, initially this page will be moved from hard disk into the RAM, right? So the page has to be read from the hard disk, right? So hard disk is accessed one time. Now once the page is moved inside the RAM, the byte which CPU want will be read from the RAM. So we are here effectively we are accessing both the hard disk as well as RAM, right? In case of page fault. So time taken to fetch the byte will be more in case if there is page fault. Okay, in case if there is no page fault, which means in case if it results as a page hit, the time taken to fetch the byte will become very less, right? That's what I want you to understand. Now, how will we understand whether this page hit or page miss? Which means the byte which CPU is asking for, whether it is present inside the RAM or not. How will we understand that? For that, we use something called as page present or absent bit of page table. We have already seen it, right? In page table entry, we will have corresponding pages property. For example, let us assume CPU is asking for a byte which is present in page 2 of P1. In this case, let us assume this is the entry which is maintained for page 2 of P1. Page 2 of, see this is page table of P1, fine, and for page 2 let us assume we have maintained this entry. Now, since page 2 of P1 is not present inside the RAM, the present or absent bit will be equal to 0. Fine. Now what CPU will do is, see, CPU before getting the byte of a process, CPU before getting the byte of a process will initially go into the page table, right, before accessing the process. Why? Because CPU needs to know the frame number. Only after knowing the frame number, it will be able to go into the process and get the byte. You know that we have already seen it. So what we want to understand is, before accessing the process, our CPU will definitely go into the page table. Now while going into the page table, we will see the present or absent bit. Okay. Now if present or absent bit is 1, we will understand that okay, the byte which we are searching for is present inside the RAM, so the time taken will be very less. Now in case if it is 0, in case if it is 1, it is page hit. In case if it is 0, the page which we are searching for is not present inside the RAM, so we might have to fetch the byte from page from the hard disk, so it will take more time. Fine. So present or absent bit is helpful in understanding whether the page which CPU wants, or the byte which CPU wants, is present inside the RAM or not. Fine. So this is one advantage of present or absent bit. So that is what I want you to understand. In case of page hit, time taken to fetch the byte will be lesser because it involves only memory, RAM access or memory access. Whereas in case of page fault, the time taken to fetch the byte will be comparatively larger because it involves both memory, main RAM access as well as hard disk access. Fine.